Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and today we're going to be talking about using voltage division and current division in DC circuits. Now let's consider a special example of loop analysis. So I've drawn a simple circuit, and I'm going to show a current direction, again going from the lower left around clockwise. And let's go ahead and write a loop equation for that. As we go around the loop, we first encounter the minus sign for the source, and then a plus sign for the voltage I've defined as VR1, and a plus sign is the voltage I've defined as VR2. So we can write the equation minus Vs plus VR1 plus VR2 is equal to 0. We also know for Ohm's law, remember Ver, that VR1 is equal to the current through the resistor times the resistance. So I can now write that as I times R1, where R1 is the resistance and I is the current through the resistor. Similarly, the current through the resistor R2 is I, so we know the voltage across that is I times R2. So we substitute in our equation, and there we have it. So here we have basically written an equation for the circuit. Now I'd like to take a step back and look at the voltage across R1, which we've called VR1. And we know from Ohm's law, that VR1 is equal to the current through R1, which is I, times R1. Okay, if we look at the equation I wrote above, right here, we know from this that I is equal to Vs over R1 plus R2. Okay, I just solved the equation for I. And now we can plug in together for VR1. We plug in I, and we find that VR1 is equal to Vs times R1 over R1 plus R2. Similarly, we can write the equation for VR2 as I times R2, which will give us Vs over R1 plus R2 times R2, which gives us our Vs times R2 over R1 plus R2. Let's do a simple example. Suppose I have a 6-volt source, and I'm going to have two resistances. I'm going to make one of them be 4 ohms and one be 8 ohms. Now, we can solve this either using the principle of voltage division or by writing loop equations and using KVL. So I'm going to first define a current going through that loop, starting at the lower left-hand corner, going around clockwise, as is my habit. And now we can write the equation minus 6 volts plus 4 times I plus 8 times I is equal to 0. Solve for I. We get I is equal to 6 over 12, which is equal to 1/2 an amp. And we can write the voltage across the 8 ohm resistor, I'll call it V8 ohms. So V8 ohms by Ohm's law was going to be equal to I times the resistance, which in our case is 8 ohms. So that is 0, it's 1/2 times 8, which is equal to 4 volts. Okay. Similarly, using voltage division, we can write the V8 ohms is going to be equal to the source voltage, 6 volts, times the 8 ohm resistor over the sum of the two resistors. So that gives me 6 times 8 over 12, which is 6 times 2/3, which will give me 4 volts if you plug it in. Now, which is easier? They're both pretty easy. I would suggest, though, that you always just go ahead and write the KVL equations and do the analysis. That way you don't memorize something wrong. Also, to be honest with you, there's very few circuits that are quite this simple. So just go ahead, learn how to do loop analysis and do it consistently, and you will be successful. Now let's consider an example that illustrates the principle of current division. We will just, first I'll derive it using nodal analysis. Let me go ahead and define this node at the top as V, and this node at the bottom I'll make a ground, which is a 0 volts. Now I can write my node equations at node V, node that's designated by V, which is also the voltage. And I would say summing the currents leaving the node, which is my preferred way to do it, I would have this current coming in, so that's minus the current going the other way. So I'll have minus IS plus the current that I'll call IR1 plus the other current IR2. These are all the currents leaving the nodes, and that'll be equal to 0. From Ohm's law, right, V is equal to IR Ver, we would then be able to plug in the current for IR1 will be equal to the voltage across this resistor, which is the voltage from node that I've called V down to ground, so voltage V minus 0. I'll go ahead and write in the minus 0, but after a while you won't need to do that. So V minus 0 over R1, and that's the current going down. Similarly, IR2 is equal to the voltage across R2, which is V minus 0 over R2. We can plug that into our equation. We get a minus IS plus V over R1 plus V over R2. I went ahead and subtracted the zeros. Will give us 0. And after a while, you'll be able to just write this equation. From this, we can solve for V, and we'll have V times 1 over R1 plus 1 over R2 is equal to IS. Let's go ahead and combine our fractions. We have V times R1 plus R2 over R1, R2 is equal to IS. So V is equal to IS times R1, R2 over R1 plus R2. From this expression of V, we can use Ohm's law to calculate IR1 and IR2. So we know from our we know from our circuit that IR1 is going to be the voltage V divided by R1. So we can say IR1 is equal to V divided by R1, which will give us IS times R2 over R1 plus R2. Okay, notice that the R1's cancel. Similarly, we can write IR2 as the voltage across the resistor divided by the resistance using, again, Ohm's law, and that will give us IR2 is IS times R1 over R1 plus R2. Let's consider an example. Here I've drawn a circuit. It's still a very simple circuit. We have a 2 amp current source, 2 resistors in parallel. And what I'm going to ask is, what is the current through the 3 ohm resistor? So that's what we want to know. And how do we figure that out? Well, we could use the equation for current division, but I recommend that instead you just do the analysis. Again, this voltage we'll call V, this one I'll call ground, or 0 volts. And we can sum the currents leaving the node V. So we'll have minus 2. 2 is entering, so minus 2 is leaving, plus V over the 3 ohm resistor, that's using Ohm's law, plus V over 5 ohms, which will equal to 0. Now we can solve for V, and we end up with V times 1/3 plus 1/5 is equal to 2. At this point, I like to keep everything as fractions. You can do what you want. If you want to put it in your calculator, keep as much precision as you can. And so we'll have V times 5 plus 3 over 15 is equal to 2. So V is equal to 2 times 15 over 8. So that gives me 30/8, which is 15/4, which is 3 3/4 volts, 3.75 volts. So now I can solve for IR3, and we know that IR3 is equal to the voltage, 3.75, minus 0, of course, divided by 3, which turns out to be 1.25, which I could have done in my head had I bothered to look instead of using my calculator. Again, that's one of the conveniences of keeping everything as a fraction, but that's what IR3 is. We could have calculated IR3 directly using current division. Remember, current division says the current IR3 is equal to the current going into the node where the current is split, so it'll be 2 times the other resistance, which in our case is 5, over the sum of the resistances. 3 plus 5 is 8. So that'll be 10/8, which is again equal to 1.25 amps. So which is the better way to do it? Well, I recommend that you just go ahead and do the analysis. That way you won't accidentally memorize a formula wrong, and it's not that much more difficult. We used to encourage students to learn all these quick tricks when we did a lot of analysis by hand. But anyway, when you see something like this, I hope you will recognize that it's current division, but just feel free to go ahead and solve the circuit instead of remembering the equation for current division. I hope you found this description of voltage division and current division helpful.